Day 7, last day of new notes. I probably won't record tomorrow. Oh, that's not true. I'll work a few of them on camera and post them.
Is tomorrow review for the test?
Okay, Unit 7, or Unit 1, Note 7, inverses of functions. So there's really only one, this is oversimplifying, but there's one main idea with inverses, and if you get this one idea down, it sort of applies to everything we do with inverses. And that is switch x and y. And you'll see what I mean when I say sort of applies to all of it, because we're going to do quite a few different things, but they kind of all come back to switching x and y. So first, a definition. Let f and g be two functions such that f of g of x equals x for every x, and g of f of x equals x. So that means if you plug x into g, you get that answer. Plug that into f, you get x back out. So that's why they're called inverses. They undo each other. So whatever g does, f undoes, and then you're back to the original. Or you can do it the other way. Whatever f does, g undoes, and you're back to the original. Let me try to draw it this way. If you take x and you put it into the g function, then the output is g of x. And if you put that into the f function, then the output is f of g of x, but I'm saying the output is just x. So g does something to it, f undoes it, and you're back to where you started. That's what makes it an inverse. They undo each other. And you have to make sure that both things are true. So I'm not going to draw the other picture, but it would be the same type thing. You would just have f first and then g. So f would do something, g would undo it, and you'd be right back to x. If both of those things are true, then they are inverses. For us, it's never going to be where one of them is true and one of them is not true, because that takes a really weird type of function to pull that off. Weirder than we want to mess with. Okay, notation with inverse is kind of confusing, at least initially. Once you get the hang of it, it won't be a big deal. But always the first time on inverses feels weird, because the notation for inverse is f to the negative 1. That means inverse of f. But the confusing thing is that's like where the exponent usually goes, right? So like 4 squared is 16. 4 to the negative 2 is 1/16. 4 to the negative 1 is 1/4. That's still true, but f to the negative 1 is not 1 over f. So it's like, come on, math people, like you should have picked a different symbol here, right? Exponent of negative 1 is already taken. We'll let that be the reciprocal. But I said, you know what, let's use that for inverses as well, and we'll just confuse all the PreCal students for years to come. So f to the negative 1 does not mean flip of f. It means the inverse of f. I guess the difference is that f and g represent functions, not numbers. So most of the time, this is not a big deal. Like, you're in a section working with inverses, so your brain is thinking inverses. No big deal. It's only like if you're on a review over like lots of things where that might throw you off. All right, graphs of inverse functions. Symmetric to each other with respect to the line y equals x, or across the line y equals x. Mirrored across y equals x. And so sort of like we did on that previous symmetry stuff, like you can fold the page, right? And if I fold it on the dotted line, those two graphs would copy onto each other. And I think you can see that for that one. You can see that for that one, maybe. I feel like you can definitely see it for this one, where the stuff copies onto itself. So that means we can do what we did earlier, and that is sort of force the symmetry. Here's a picture. Draw the rest of the picture, or just draw the inverse. So that means I need to copy what's there across y equals x. Now, some people are good enough to like visualize what's going on and just like put a pretty good sketch on there. just by eyeballing it. That's not me, so I'm going to assume it's not all of you. So I'm going to go point by point a little bit here, at least until I figure out what's going on. So that point's 0, 2. If I want to flip it across x, right, this line is y equals x, which means x equals y, which means switch the x and y, what I said at the very beginning. So 0, 2 becomes 2, 0. And then let's pick another point to reflect, preferably some integer points. So 2, 6 I think is a good one. That would become 6, 2. And if you needed to plot more, you could, but maybe by now you've got a sense for what it looks like. And we got a few points on there. Something like that. By the way, we don't do this for all of them, but we can do it on this one because it's simple enough. How about the equation of that original function? You know what that equation is? Can you tell by looking? Maybe if I had put an extra point on it, it would have been a little more obvious. What's the basic shape? Not of this one, but of this one. Oh, I know. Yeah, because we didn't use all of it. Maybe that helps. So that's x squared moved up to. Now this is a little bit tricky because we didn't use all of it. We'll talk more about that later. What about this curve? What's it? Square root. Yeah. So inverses are supposed to undo each other. We've got an x squared and a plus 2, and we've got a square root and a minus 2. So it makes sense that something is going on here where those are sort of canceling each other out. It's pretty rare that we could do that where we could pick off the equation. We're not going to do that on the next two. Let's just pick some points. So negative 2, 0 is a good one. Which means 0, negative 2 is sort of its corresponding point. I contend there's some like free points on this one in terms of reflecting across y equals x. There's like 2 points that are like freebies in terms of reflecting. You know which points I'm talking about?
Oh, the points that hit the line of symmetry.
Yeah, the points that are on the line of symmetry. If you folded it, those points aren't going anywhere. So maybe that's enough, those 2 points plus this point, and just sort of visualize what's going on here. Something like that. So those are inverses. And then the last one, again, the point on the reflection line is a free point. It's on both of them. And then pick some point that's easy enough to reflect, like 0, negative 3. Becomes negative 3, 0. And it's a straight line, so we shouldn't have to do any more than that. And now we've got a picture of inverse functions. They switch their x and y. Yes, sir. I'm not going to grade arrows on the end of line, especially on these because the original didn't have an arrow. So if I was going to grade, I should take off if you put an arrow, right? Because the original didn't have an arrow. But if that becomes an issue, I'll let you know. But on this one, the original didn't have an arrow, so the copy shouldn't. All right, the way this is written implies these go together. I don't think they go together, so I'm putting a hard line right there. To me, that first dot applies to the graph. If f of b is on the graph, then b of a is on the inverse graph. That's what we just did. I'm going to mark out the word so, because I don't think they go together. To prove or verify that two functions are inverses of each other, we'll use the definition of inverses, which is f of g equals x and g of f equals x. And you have to show both. Okay, you can't show one and be like, if it works for one, it probably works for the other. Yes, you are right, but you have to show both. So g of h. So I'm going to have to do two things. I'm going to set them up first, mainly so I don't forget to do one of them. It's a little bit of work, so by the time you get through one of them and realize that it works, you're thinking, yes, I'm good. But you got to do both. So both of those should be x. And the fact that it says verify means that they will be x. Right? I'm not going to tell you to prove and then make it a trick question where it doesn't really work. If I ask you to prove or verify, it's going to work. So g of h is kind of a mess. Cube root 3/2 x plus 1. So that means all of that h function is now the input to the g function. The g function is 2/3. That's kind of how I like to do it sometimes. 2/3 times the input cubed minus 1. So if the input was 3, we'd put in a 3. If it was 7, we'd put in a 7. If it was pi, we'd put in a pi. If it's cube root of 3/2 of x plus 1, then, well, in that goes. Now, this is where the fun starts, but you do have to show your work here. So what can I do first on simplifying this ugly thing? Cancel what? Be careful. What can we cancel? The cube and the cube root can cancel. So now I've got 2/3 times 3/2 times x plus 1 minus 1. 2/3 and 3/2 can cancel. At some point, I don't need to write this out every time. Plus 1 and minus 1 cancels, and we're back to x, which is what we knew we were supposed to get. We just had to show how to get there. Which means you guys that like to skip steps, you've got to show something. Like, I know what the answer is supposed to be. You can't just up here at the beginning say equals x, good. Like, no, I have to see the process. And you may not show as many steps as I've shown, but at least show enough that I can see where things are going to cancel each other out. All right. Again, for us, if it works for one, it's going to work for the other, but we got to show it. 2/3 x cubed minus 1. So cube root 3/2 of whatever the input is plus 1. So like the order of canceling is different on this one, but it's the same kind of thing. Like the 3/2 and the 2/3, those cancel. And then then the plus 1 minus 1 cancels. And then we're left with the cube root of x cubed, which is x. Which is what we knew we would get 5 minutes ago. The main issue there is make sure you show both of them. Like, it's not hard, but I think people just get excited to show one and they get all the algebra right and it's fun to cancel everybody out, and then they forget about showing the other one. So make sure you show both. Okay, so that was the verify problem, or prove. The next thing we can do is find an inverse. So instead of giving us two of them and asking if they are inverses or showing that they're inverses, they give us one of them and ask us to find the other. Switch the x's and y's. Except that doesn't have a y in it anywhere, sort of. What do I mean by sort of?
Can you just put the x on the outside and put negative, or put y in for it?
Yeah, y is pretty much the same thing as f of x. So that's not an inverse yet. All I did was switch out the y for f of x. So in place of y goes x. In place of x goes y. Everything else stays exactly the same. Everything else stays exactly the same. Replace y with x, replace x with y. And that is the inverse. But we're not done with the problem yet. What have we not done? Solve for y. So let's see here. Now it's just like peeling away all the layers to get to y. So how many layers do you want to peel at once? I'm going to peel them one at a time. You peel as many as you think you can get away with accurately. So x minus 5, and then I'll divide by 3, and then I'll cube root. So if you want to do 2 in a row or 2 at a time, x minus 5 over 3 cube root equals y minus 7, and then move the 7 over, and there is my inverse. You don't have to label it as an inverse, but on a multiple choice test it will likely be labeled as the inverse, so make sure you recognize what that means, what's going on. Alright, you can't really check it by inspection, but you can halfway check it by inspection. And by that I mean, look at all the things that are going on in the original and see if the opposite things are going on in the inverse. Let's see, times 3 divided by 3, plus 5 minus 5, minus 7 plus 7, cube and cube root. So, who knows exactly if they're on there in the right spot, but at least they're all there. Yes?
Will the test become if we put y then? The inverse of y?
I'm going to say no, because it asks for you to find the inverse, and so if your only answer is this, then I'm assuming you're telling me that that's the inverse. Again, multiple choice would probably have it there, but they'd probably all have it there. So switch x and y, solve for y. Algebra fun. Okay, let f be a function. This means it passes the vertical line test. Each x gives only one y value. This would be the good old vending machine diagram. So my vending machine has 3 buttons. If you push button 1, you get a Coke. You push button 2, you get a Sprite. You push button 3, you get a Sprite. Is that a functioning vending machine? Yes. Good. No one answered no. First class of the day to pull that off. That is a function. How would it not be a function? What would make it a non-functioning vending machine? Correct. If you get 2 outputs, or either or, you don't know. So like if you push the 1 button and you get a Coke or a Sprite or both, that's not hey, congrats to you, you got a free drink, but that's not a functioning vending machine. So you can have multiple buttons going to 1 output. That's fine. That's still a function. No y value is repeated. That's for the inverse. If the inverse of f is a function, so inverse means go backwards. Well, if we think about going backwards, so you walk up to this vending machine and a friend of yours is standing there with a bottle of Sprite. Can you go backwards and know which button he pushed?
No.
Or she pushed? No, because if you're going backwards, there's now 2 y's, or 2 x's, I should say, and you don't know. You don't know. So if you want it to be 1-to-1, here's where you'll see where that name comes from. So that's a function, but it's also a 1-to-1 function, meaning I can go backwards. Right? If someone's standing there with a Coke, I know they push the 1 button. If they're standing there with the Sprite, they push the 2 button. Standing there with Dr. Pepper, they push the 3 button. So that function has an inverse function. That function has an inverse function. This one is not one-to-one. It does not have an inverse function. You can't go backwards, at least, and be a function. So this one-to-one business, it's hugely important in later theoretical mathy stuff that's way beyond what we want to do, but that's why we kind of introduce it now. The shortcut, thank you. The check for one-to-oneness is the horizontal line test. So that sort of makes sense. To check one way is the vertical line test. To check the other way is the horizontal line test. Number one, which of the following functions is one-to-one? So this one, let's check vertical line test first, but we're definitely good there. How about the horizontal line test? Yeah, any horizontal line you draw is good. Only crosses once. So that is a one-to-one function. Graph of G. Does it pass the vertical line test? Yep. Vertical line test. Check. It is a function. Does it pass the horizontal line test? No, it does not pass the horizontal line test. Right, so if you're thinking backwards, if you know your y value is 3, and you want to know, well, what x value gave me that? I don't know. I can't go backwards. So it is not one-to-one. Thank you. Kinley. How about H? Without drawing all the lines. Yes or no? No. I mean, same reason. It doesn't pass the horizontal line test, but it is not one-to-one. So F is the only one. Again, there's lots of theoretical stuff that can happen if there's a one-to-one match on inputs and outputs, the ability to go backwards. That's about where we stop with it. Which of the following functions is one-to-one? So I don't have a picture. I have an equation. But I still think in terms of pictures. What's that first graph look like? Or what is that first graph? Parabola. Is that one-to-one? No. Second graph's a square root. It's been moved left 4 and down 2, but that doesn't really matter in terms of one-to-one stuff.
No.
So is that one-to-one?
No. Yes.
Any horizontal line I draw only crosses once. Now C, you might not know what that is, but that x squared is, those even powers, they like to mess things up. Because if I input -2 or 2, I'm going to get the same thing out, right? Because I square it right away. So that's not going to be one-to-one. I don't know what I get if I plug in 2 and -2, but I get the same thing. I mean, it's not hard. Square root of 5. So that x squared messes up the horizontal line test. D. I don't know what that... Well, actually, I do know what D looks like. What is D?
Parabola.
It's a parabola. It's a downward parabola. I have no idea what it looks like. I shouldn't phrase it like that. It's a downward parabola. So that's a pretty good idea what it looks like. So that's not one-to-one either. So only B was a one-to-one function. Again, that's sort of where we stop with it, but there's lots of interesting things later that work out because of it. 158. Oh yeah, we're good. Because because inverses, let's just put it that. Because inverses, we know something about the domain and range. with inverses we switch x and y. So even without knowing an inverse, I can know an inverse's domain and range because they're just going to trade places, because domain goes with x and range goes with y. So the x values of the inverse were the y values of the function, and the y values of the inverse were the x values of the function. Does that make sense? Like, there's weird words and fancy words, but it's like when we were doing the graphing and we switched the a's and b's, or we switched the x's and y's, we did that for all of them. So everything that was an x for the original became a y for the inverse. So everything that was a domain for the original became a range for the inverse. So example, if m of x equals this thing, find find the inverse of m. But I'm going to mark that out because I can find the domain and range without knowing the inverse, because of the switcheroo thing with the x's and y's. So let's set this up. We want to find the domain and range of m and its inverse without even finding m. All right, I contend the domain isn't too bad for m. What do you think? What can't x be? -9/2 or -4.5? Because that would be dividing by 0, and we can't do that. So we got this big set of x values. In fact, all of them except for one thing. So we switch the x's and y's. So what do we learn about the range for the inverse? Okay, can't be -9/2. Be careful. What can't be -9/2? The y's, because the x's and y's traded places. So I know the range of the inverse without really knowing what the inverse even looks like. All right, how about the range of the original? That's a little bit trickier. Remember do you know what the parent function of this thing is?
1 over x.
Yeah, 1 over x, the reciprocal function. Let's see, we moved it left 9/2. So that changed that asymptote. Did we move it up and down any? No, I mean, we stretched it, but that didn't change where the asymptote is. So no up and down movement or translation. So that means it's still everything except y can't be 0. Which means I don't know what the inverse is, but I do know something about the domain of the inverse now. Did the same thing last time. What can't be 0? X.
Do you write this down? Do you write it like that, or do you write it in a
So I'm kind of doing the lazy way because I think it's easier to talk about the concept by not spending 5 minutes writing parentheses, 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 infinity. Yeah. So if I don't specify, then this is fine. If it's multiple choice, it's probably going to be a little more formal, and it's going to be an interval notation. But just because I want to get to the heart of the matter, and I think it's easier to see the concept written like this than if you write it out, all of the parentheses. And, well, no brackets, but lots of parentheses. Random practice problems. Let's see. G inverse of G inverse of 3. Well, that means I would need to find the inverse of G and then do G inverse of G inverse of 3. Basically, I'm not wanting to do all of these, so I'm trying to see if there's one that looks better than the other. If w of x equals 9x to the 4th, find the inverse function if it exists. If the inverse function does not exist, state why. I think I know why it doesn't exist right now. Do you know why? We ran into this problem earlier with the vertical line test. What's going to happen when we solve for y? We're going to get a plus or minus. So forget the details. Eventually I'm getting the plus or minus the fourth root of something. So not a function. At least the inverse is not a function. The original is a function, but the inverse is not a function. Lastly, average rate of change. So that's change in y over change in x, but of the inverse. So you got to find the inverse of p and then do the average rate of change. So it's kind of just two problems sandwiched in one. All right, today's assignment is worksheet 6. Tomorrow is worksheet 7. Tuesday. No new information tomorrow, but again, I'll record, and I'll try to record at least one new problem per class so that everybody can see more problems than they would have seen otherwise. And then block day is the test.
What's due on block day?
What's due on block day is the rest of the worksheets, 4 through 8. That means for you, well, it's less of a problem for you guys because I don't see you till Thursday. But, right? 6th period, yeah. You know all the information to get started on worksheet 8 because there's nothing new there. It's just applications. And so if you already know that your Tuesday night and Wednesday night are booked with whatever, then maybe Monday night needs to be the day you get 2 worksheets done. Again, it's not as big a deal for you because you got multiple days. It's those odd people, at least people in odd classes, that have to be a little more worried.